Thank you very much. So I'll talk a little bit about Creusot. It's a good thing that we're doing a more casual thing. So I kind of put together slides of both past things that have been done with Creusot, current things, and sort of future things. So we can go through them, and then I'm happy to answer any questions about anything other that I haven't covered. I also didn't quite know who the audience was going to be, so in case you don't know too much about what verification is and why we want to verify it, right? And why verifying in Rust particularly is interesting, right? So traditionally, with verification, there's sort of two problem domains where it's kind of been found. One is like very low-level stuff where you have small little programs doing complicated, nasty things to your computer, and you want to make sure that those complicated, nasty things are correct, right? And then on the other side, you have much higher level programs, like maybe a compiler, right? And you're going to verify strong properties about those programs, and typically because you're working usually in a pure functional language, something like Rock or something like that, you can reach a higher scale of program size, right? Maybe thousands of lines of code, but you often lose a lot more control about what the machine is actually doing when it's running your program, right? And the thing is, of course, that those two categories of programs are a very, very, very small fraction of all the programs that we write out there, and even a very small fraction of the programs we would like to verify, right? So why Rust? Why do we care about Rust in this context, right? Well, the reason is Rust is actually kind of both of those halves, right? So in Rust, you can go all the way down to the machine, right? You can do all your unsafe stuff, manipulating raw pointers, causing UB all over the place, right? So like, I don't know, this is a sample of code from Vec, I think, that's just reallocating the internal vector. And then you also have a really nice type system and a bunch of cool language features which let you work instead at a much, much higher level, right? And so you can also just work with iterators, right? Like a very common feature of Rust is we love iterators, we love chaining iterators, we love closures as well, mapping things, filtering, all this fun stuff. And so this combination of features has meant that Rust has very quickly moved into a lot of like the traditional targets of verification. So things like operating systems. There's a lot of operating systems projects out there written in Rust. Databases, I actually work on a database professionally now written in Rust. Critical systems more generally, any sort of important piece of software where you're a little bit scared of the guarantees provided to you by a language like C, right? But it's also sort of expanded the scope that systems languages traditionally are used for, right? So you have a lot of sort of applications that are just written in Rust now because the language itself is so nice to use. The Rust type system also makes concurrency a lot easier to work with. So you see a multiplication of concurrent programs, things where people would have been hesitant to use concurrency. Now they're like, well, I could just do, std thread spawn, whatever, I'm fine. The Rust type system will get me. And so a lot of programs that might have been sequential before become concurrent. And all these things also expands the scope of programs that might want to be verified. And this observation has been noted by quite a few teams out there, right? So there's been a lot of Rust verification projects that have popped up. And this is just a small sample of the projects. There's plenty more logos that could go on this screen. And a lot of these projects have made the observation, furthermore, that the Rust type system in particular it has a role to play here, right? Like ownership types fundamentally make reasoning about programs in a formal way a lot simpler, right? And Creusot is one of those tools that also is based on this observation. So the idea that ownership types will really simplify reasoning, right? And what ownership types allow us to do in Creusot is that we can translate Rust programs into a pure functional language and then verify that instead. The reasoning being that verifying pure functional programs is generally considered to be a lot simpler than verifying imperative mutable languages with memory and pointers and things like that. And we'll talk a little bit about how exactly we're able to translate a imperative language with mutable pointers and all that stuff into a pure functional language with none of those features, right? But first, a little bit more about how Creusot works, what it does, right? So at a high level in Creusot, you take your Rust program, you write pre and post conditions. So you can see those in the little brown brackets above my heap sort function. And those pre and post conditions are written in a specification language. We call ours in Creusot Perlite. It's effectively like a functional subset of Rust with some additional fancy operators like quantifiers and things like that. We take all of that, we run it through Creusot. It generates a functional program in a language called Coma. That language is understood by a verification tool called Y3, which will take your Coma program, generate a bunch of logical formulas that imply the correctness of that program, and throw them at SMT solvers. or other verification backends. And if all those solvers agree that the obligations are upheld, then you can be confident that your source Rust program actually satisfied whatever property you wanted to prove about it. Right, so yeah. So how do we handle Rust borrows? First, maybe let's go back over what is the problem with pointers in traditional C languages, right? C-like languages, right? So if we have something like this memcopy function here, I should also say, if you guys have questions along the way, feel free to interrupt me. I'd be happy to answer questions as we go through things here. So let's take a memcopy function, right? So all we're doing is we really just want to copy from source to target, right? So what are the problems that are lurking in this 3-line C problem? Well, at a very basic level, pointers have very few guarantees, right? So these two pointers could overlap, right? In which case memcopy is sort of ill-defined in the first place, right? Moreover, the pointers could just be uninitialized, right? And so then you're going to segfault when you try to read from them. And you could even have stuff like going out of bounds. Nothing guarantees a relation between size and your pointers, and the compiler won't do anything, the C compiler won't do anything in particular to help you maintain any sort of properties about that, right? So that means that when you want to reason formally about a C program, you have to account for all those possible behaviors, right? You have to prove that your program does not do any of those things. And so typically we have a bunch of powerful tools to do this for C. You know, with things like separation logic, we can really reason about, oh, target and source are two disjoint regions of memory. They're both initialized, all these kinds of things. You know, they point to arrays of at least size and length, all this kind of fun stuff. But this is all sort of tedious. It also means that the reasoning is a lot more complicated. Separation logic tools have a lot more work to do than equivalent tools for pure functional languages. And this just kind of complicates your work. You don't really care, you don't want to care about all these kind of layout considerations when you're just trying to verify your code. And if we just translate our code to Rust, right, we have something that looks very similar, but has very different semantics all of a sudden, thanks to the Rust type system, right? So all I did here is I took the same code, right, and I just used Rust types in various places, and this comes with a lot of guarantees. In particular, right off the bat, we know that our source and target have to be disjoint because Rust has this nice property of mutability XOR aliasing, right? So if you have a mutable pointer, you have a unique mutable pointer to that region in memory, right? And if you have a shared pointer, that one could be shared, but nobody will modify the value that you're pointing to, right? So you can be pretty safe here knowing that source and target are going to be disjoint, so you don't have to worry about anything overlapping. Additionally, Rust has this thing that, you know, safe Rust programs should not be able to observe UB. And so as a side effect, that means that your pointers have to be initialized, right? So you also know that you're allowed to read whatever is in source and target. And this doesn't necessarily help verification, but the Rust compiler also even just checks that you know your source array, every index to your like every time you access the array, it's going to check that you're accessing it within bounds, right? It's not going to just let you start doing crazy stuff. Though of course, in general in verification, we'll want to check that the access is in bound to prevent crashes of your program. And all of this just means that right off the bat, we've eliminated a lot of the things that we would have to prove to even start thinking about our C program, right? These are just things that are handled by the Rust type system for us. So we don't have to consider any of these things. So how do we take advantage of all this to actually verify Rust programs? And the trick is basically that Rust is actually sort of, if you squint and look carefully, a functional language, right? What I mean by that is that we can actually sort of interpret all of our Rust programs into equivalent functional programs that preserve the interesting semantics that we want to see in verification. So if I take a function like this increment function here, which takes two inputs, x and y, adds the value of y to the x, and then returns this x value, I could write it in any sort of camel-like language, right, as a function that takes x and y, rebinds x as the sum of x plus y, and returns x, right? Those seem equivalent to everyone, right? But so far this is really kind of boring, right? We're just talking about adding integers. We've known that that's easy to do in functional languages, right? So we could start adding things like pointers, right? So in Rust, of course, we have box, which is, you know, an owning pointer. So the box owns the integer it holds, and we write the same code, but this time we're adding inside of pointers, right? So we're adding the value pointed to by x, or the value pointed to by y to the value pointed to by x, right? And returning the box x. And so how could we encode this in a functional language? Well, the idea that Creusot is built on is that we can just ignore the box, right? Because the box is unique, it has, nobody else can observe the value of x. If you're holding box of this box, nobody else can see what's inside of it, right? So for all intents and purposes, you could pretend that the box is not there, right? You can just treat it as its contents. And so we can do the exact same encoding as we did before. Of course, the problem is if we're only talking about owning pointers, again, that's still not very interesting, right? That's basically the same thing as just having a value. You just have a, it's not on the stack, it's on the heap. You just have a pointer to the heap location. Nothing very fun is going on there. So we could look at what happens when we have shared borrows instead, right? So now all of a sudden, x and y could be the same thing, right? So how do we model this situation? And the code is slightly different because, of course, we can't mutate immutable borrows in Rust. Well, once again, we can do the exact same thing as before. And this is, again, because the Rust type system tells us either you're mutable or you're aliased, right? So we don't have to worry about the values of x and y changing beneath our feet here, right? So we can just say, we'll just treat x and y as a thing that they point to. We don't care about the identity of the pointer itself. And of course, we get to sort of the pièce de résistance in Rust, which is mutable pointers here. We are going to have a reference to some other value. We want to mutate it. And eventually, somebody else will see that we mutated it, right? So we can't get away with all the tricks that we had before, right? And so I rewrote the same thing, and I also wrote a little function that actually uses our mutable pointers so that we'll be able to see how the whole thing goes together, right? And so if we tried to, like, the issue here is, of course, that when we pass our mutable borrow x here, when we pass it into incremute, how would we model that as a functional language? We don't have mutation. We're assuming we don't have any sort of reference or anything like that in our ML language. We have a pure functional language. So how can we actually model this, right? Somehow, at that site in main, we need to give something to incr such that afterwards the value of x has been changed, right? And that's going to be the tricky thing. And the tool Creusot uses to work around this is a prophecy. Basically what happens is there's 2 points that we care about, right? So this very first point here is the moment we call incremute, basically. We give our borrow away, right? And at that point, we know what value is in the borrow. It's whatever value we had when we originally created our borrow, right? And then something happens, and eventually we need to figure out the value that the borrow had when it expired, right? When the borrow was tossed away. And the idea of the prophecy is then rather than trying to figure out, like to thread through all the execution of your code, which might include loops, branching, function calls, all these kinds of things, and figure out exactly what value this individual borrow had when it was thrown away, we could just sort of flip things on its back and just say, we can prophesize that out. We could just guess the correct value ahead of time and update the variable x that we want to see. So in particular, to implement this, we can use non-determinism. So the idea is going to be, we have two sort of gadgets. One gadget that represents the creation of a borrow. And so we're going to model individual mutable borrows in Rust as a pair of values, a current value that's being held, like the thing that we're pointing to, and a final value, which is going to be a thing that will eventually be pointed to by that borrow, right? And so we create the borrows as a pair, and we guess some final value for that borrow, right? And then what we do is we immediately update the lending variable with that final value. So that lending variable already now has some value from the future, right? And we do all of our normal calculations. We update the thing that's currently stored in that borrow, et cetera, et cetera, et cetera. And eventually we throw away our borrow. And when we do so, we're going to put this assume instruction. And you know, the assume is going to be the dual instruction to assert. It's going to say every trace that reaches this point, for every trace that reaches this point, this fact must be true. And that basically has the effect of constraining our prior choice, right? When we made that non-deterministic choice earlier, we had to have chosen some value that would satisfy this assume later on. And that basically means that we can sort of time travel a value back to the moment that we created our borrow. To make this all a little bit more concrete, here's our example from earlier with the function called inlined into main, right? So we have the moment we create our borrow here. So we create let x is a mutable borrow of a, right? And as I said, we're going to first pick some non-deterministic value for the final value here, this any, and we're immediately going to update a with that final value. So a now has some value, right? It's some prophesized value, that the final value of x, right? And we do our normal calculations, so we're just going to update the current value of x with whatever is in y, right? So we're going to increment x like we would with any other sort of pointer type. And eventually, we're going to get to a stage where we're going to get rid of x, right? X goes out of scope, whatever, the lifetime ends. And at that point, we're going to insert this assume instruction that says the final value of x must be equal to its current value. And that sort of tautologically makes sense because we're done with x, so whatever its final value must be its current value, right? But because of that, we now know, so that we know the final value of x is its current value. We also know if we read the code that the current value of x is 10, and we also know that a is now the final value of x. And so from that, we can easily conclude the thing that we cared about, which was that a is now 10, right? And all of this, where on the right-hand side, we have a pure functional language. We don't actually have any sort of references or anything like this. And this is a language that we can very easily verify. We know this is like, very standard kind of target for verification. There's a lot of tools out there that can handle this kind of stuff, all right? And so this gives us the brick to sort of model the core Rust language, right? From this, we can do values, sum types, everything, all the types of Rust. We can do all the pointers of Rust, all these kinds of things. But there's so much more to Rust than just the mutable borrows, right? In particular, idiomatic Rust code loves to make use of all sorts of fancy features like higher order functions, iterators, in practice also futures, right, which are just kind of another form of iterators. And soon there's going to be coroutines and all these kinds of things. We love complicated abstractions that let us work at a higher level semantically and yet compile down to efficient machine code, right? But these abstractions are often sort of bad for verification purposes, right? Like the more when you start introducing higher order functions like Rust closures, which on top of it can do stuff like mutate borrows internally each time. You could have a closure that counts how many times it's called, things like that. These are all the kinds of things that we don't really like in verification because it complicates the reasoning about who updates what is the value of all of our individual variables. But the very nice thing is because we're able to do this encoding of Rust borrows and everything into a pure functional language, we can actually even extend that encoding to closures. All these things can be modeled purely at a functional level, and it eliminates a lot of the concerns we would have when verifying these kinds of features in other languages. So let's look a little bit at the case of iterators here. So I'll talk a little bit about iterators and closures because we've done quite a bit of work supporting these kinds of things in Creusot because we'd like to be able to verify something that resembles idiomatic Rust code. And so we want to make sure that working with idiomatic Rust tools doesn't pose an undue burden on you as a verifier. So what is the challenge with an iterator, right? So one, things like iter will create references to some vector, but as we saw, like references shouldn't be so scary, right? Like we can kind of erase most references. We could just say, oh, this immutable reference is just going to be the ith value of v, these kinds of things. It gets a little bit trickier when we start looking at things like map, right? Because map is an iterator that takes some closure, applies it to some iterator, and returns that, right? And you have to reason about whether or not you're even allowed to call that closure on the value that you're given, all these kinds of things, because maybe your closure says something like, if I is less than 10, panic, right? So how do you prove that I is never less than 10, right? These kinds of things. Or the closure could just be modifying arbitrary values, right? It could be updating things without, you have to be able to reason that all these things are safe for your program to do. And then also you have things like collect, right, which will execute your whole iterator. And in fact, that's basically hiding a for loop internally, right? It's going to be doing a whole loop that's going to be accumulating some value, doing complicated stuff. And in some sense, is hiding an inductive proof there, right? Because it's going to have to reason about what each individual call to your iterator chain has done to the state of everything around it, right? And so all these things are kind of nasty. But the really cool thing is that using our approach to iterators, all this can be, this code here can be verified fully automatically with no additional assertions, no additional reasoning. And so, I mean, in this case, the proof is pretty banal, where you just say that the vector W that you produce is just one more than every cell in the vector V, right? So how do we actually model iterators in Rust? So in Rust, we have the iterator trait, of course, which just has a next method that optionally produces a future value and a type of items that that next method produces, right? And as we saw earlier, we have a bunch of combinators that we can be used to build up more and more complicated iterators from simpler parts, right? So however we go about modeling iterators, we want there to be a tool that is both composable and generic, that we can specify and prove individual iterators correct and know that all their combinations will also be correct, or at least you will be able to reason about the correctness of all those individual combinations without having to consider the whole each time, right? And so in Creusot, we ended up adding support for traits a long time ago. And in particular with traits, we can have these predicate clauses. And so these are clauses that we can use in a trait that will allow us to define like Creusot specifications for individual things. And so for an iterator, for example, what we do is we have two predicates that describe an iterator, and we sort of treat it as a transition system. So the idea is we have one clause completed that sort of describes like the accepting or final states of our transition system, what it means for the iterator to be finished, right? Kind of intuitively. And we have the second, more complicated one, produces, that captures what it means for what is a valid sequence of transitions. And so the idea is, for example, and I'll give some examples in a second, but the idea is going to be that like we want to say, from some initial state of the iterator, what items can I produce to bring me to the final state, right? Any questions so far, by the way? No? Yeah?
Yeah, maybe you could talk a little bit more about the implementation of the assume, which is probably key to many of your proofs when they run automatically.
Yeah. I mean, it just comes down to like a standard assume in the WP calculus. Like at the end of the day, that's all we're doing is we're taking a basic like functional language with assert and assume, right? So the same way that assert is going to generate a, what is it? Like assert of. Yeah. But assume is going to basically become a precondition. It's going to become an implication, like a free hypothesis, right? Like, yeah. So it's not. I mean, I could write it down after the talk. I think it would be simpler. But yeah. Okay. Yeah. Right. So we can define this for iterators like iter here, right? So for iter, the essential thing that we say is that iter is completed whenever the thing that we're iterating over is empty, right? So this self at equals sequence empty is Creusot speak for the value being held by this iterator is empty. And we can describe what it means to be a valid transition or a series of transitions for this iterator. And roughly what we're saying here is that if we view self as a sequence, then that sequence must be equal to the elements that we produced with the sequence represented by the target iterator, the end state that we're in, right? And to make it a little bit more concrete, right? What we're saying is if we have the sequence, we're iterating over the vector 1, 2, 3, 4, 5, right? Then what are the valid transitions? What elements can we produce that would get us to the vector 3, 4, 5, right? And I mean, I think everybody can figure out that it's 1 and 2, right? So we're able to define these kinds of things. And the really cool thing is that this tooling, this approach actually extends to a lot of Rust iterators. I mean, so far we haven't found any iterators that cause any issue, and we've proven quite a few of them correct, right? So from this, we're able to prove things like iter mute, where we basically do exactly the same thing as we did with iter, except instead of saying that we're producing individual immutable borrows at each step, we just are producing mutable borrows at each step. We can also prove much more complicated things like map or filter, where we have to reason about what the closure is doing to its own captured state. Each time you call it, you have to sort of build up this chain that says, the first call of the closure produces a state that can allow you to call it the closure a second time, which produces a state, et cetera, et cetera, et cetera. Filter, chain, skip, enumerate, take, drop, take. All these kinds of iterators can sort of be specified in the same way, right? And so the produces relation just describes what does this individual iterator do. And when you combine all these things together, all these produces relations, we have some additional sort of side conditions that we impose on them that allows us to reason that their combination is itself a valid iterator with a valid production relation. And all of this is sort of made possible, again, by the fact that like we eliminated so much of the reasoning that's necessary by working in Rust. Yeah?
Will that solve with onsite?
That's actually the next thing I'm going to talk about. Yeah, one thing I should mention here is all these guarantees of the Rust type system are, of course, guaranteed only really in safe Rust, right? It's lucky that most Rust is safe out there, right? So most of the code people are writing and care about is safe. It builds on top of unsafe layers, but is itself safe. Right. Yeah, and all of this is sort of made possible by this very, very strong type system, right? One thing I won't talk about here is when we looked at this, the closure here, we don't actually have to give any sort of specification for the closure. We don't have to reason about, the pre and post conditions of this closure or like what it's doing. Creusot is able to actually sort of infer that behavior from the body of the closure. And that, again, leverages the fact that Rust simplifies reasoning so much to just a functional language that it is much, much simpler to implement than it would be for a different language. All right, so, yeah?
Maybe before we go to the unsafe part, so I probably missed this.
Yeah.
What is Creusot using under the hood? What is this functional language?
Yes, so we target a language called Coma, which is a front-end language of Y3. Yeah, so Y3 is a verification platform that basically ingests a bunch of different languages and outputs verification conditions for like 15 or 20 different solvers.
So you have like a big semantics of Rust in Coma, basically.
Not even. We really it's internalized into the Rust compiler. So we really produce a functional program that, I mean, on the side we've proven should have the same semantics, right?
So
Yeah.
The translation from Rust to Coma is justified by the properties of
Yeah.
Rust.
Yeah.
Held up by safe.
Yeah, and a while ago we worked on a paper called Rust Hornbelt, which sort of proves correct the foundations of this approach, right? The idea that this model is correct, that you can interpret Rust programs as, in the case of Rust Hornbelt, directly logical formulas, but yeah.
So if you wanted to, so you have like an argument basically that this transpilation or this cogen is correct.
Yeah.
Is there any way to test it directly, like to take the Coma code and execute it on tests that are Rust programs and see they're getting the correct output, or to even verify the cogen? I mean, verify the cogen would be, maybe you could use Creusot to do it, I don't know.
I think unfortunately we have a little ways off before we can verify the cogen still. I do think actually that there might be a PhD student who will sort of work on that will be starting a thesis next year that's subject is basically that. But when it comes to actually executing Coma, yes, it does actually have executable semantics, and Y3 has an interpreter for it. So you can literally run your Coma code. You could also just run like the verifier on your test case and prove that none of the assertions fail, right?
Well, I think
but yeah.
run the verifier.
Like, I mean, you could just, do proof generation on your test case. And so by default, the proof generation is going to prove that you never panic, which means that you have to satisfy all your assertions.
Yeah, I guess I am more interested in knowing if like the kind of semantics that's built into this compiler is correct, I guess.
Yeah.
To me, like testing the output Coma code seems like the most direct way to do that. Just like on a large body of Rust programs, and make sure you get the same output as.
You could definitely do that. It's not something that we've done, though.
Okay.
Yes?
Along the lines of an earlier question assumes,
Yeah.
assumptions. So for Havocs, which I think are not inherently in every functional language, so how do you do with Havocs or non-determinism in Y3? Is that a first-class citizen?
Yeah. Yeah, the code I showed example is literally the code that is, like, those were real Y3 snippets, basically. Just the any keyword will produce a symbolic value, basically, in Y3. Yeah. So that's what we do. Yeah.
So I'm not sure if like a language like Clock or other language that we use.
You can embed that, like, for example, you can use the non-determinism monad in Coq to have something like that, right? Like, and I'm sure there's a bunch of other fancier techniques that people more expert with those tools would use today. And for example, in Rust Hornbelt, we modeled that by directly translating to logical formulas where we can just use a for all quantifier to basically say, like, we're reasoning for all possible values v such that v satisfies some side condition, this thing is true, right? Yeah. Any other questions? Okay. Right, so approaching unsafe, right? So what we saw so far, it works for safe Rust, right? And obviously, while most Rust is safe, it, one, builds off unsafe layers, right? And second of all, even in your safe program, eventually you might have like 5 little lines of unsafe that you need to write. Some function that manipulates a slice in some nasty way, some trick that you need to pull, right? And so you want tools for when you go there. And so basically here, we might want to verify something like this, right? We just want to do some very basic pointer assignments, right? So in this case, we just want to assign 42 to some raw pointer and then assert that we assigned 42, right? That shouldn't be too much to ask, right? In Creusot, we'll actually see we have 2 different ways of sort of tackling this problem. The sort of main way that we've been working on is ghost code. So the idea is we're going to add additional code that doesn't exist at runtime in your Rust program, but does exist at verification time. And that additional code can be used to provide sort of the missing information to the missing safety argument that's left implicit in the Rust code. So for that, we actually have 2 kinds of ghost code to make things a little bit more complicated. We have snapshot, which is really just like it's taking a snapshot of some value and it's lifting it up to the logical level. It no longer exists in Rust, right? It's just image of the Rust value at some point in time. And ghost, which is closer to Rust, it is a normal Rust value. It has all the normal Rust obligations of moving and ownership and all this stuff like this. But when you compile your program with cargo build, it won't exist. But when you do it with cargo Creusot, it will exist. That's sort of the essence, right? And so in particular, if you move out of a snap variable, you're allowed to move. You're allowed to do it. You can treat everything that's snapshot as copy. Whereas if you move out of a ghost variable, you moved out of a variable, you can no longer use your old ghost variable, right? And this is very similar, by the way, to linear ghost code. This is basically, we built this in large part inspired by Varus, right, which is a tool that introduced the idea of linear ghost code for Rust verification. Though there are some twists particular to Creusot, but that's not, the essence of the idea is very clearly from Varus. And so with this, we basically we can introduce a new type of owned pointers, right? And when you create an owned pointer here, this ptr own new, you get back 2 things, right? One is the raw pointer, and then the other is this ghost token that sort of represents your ownership of some given raw pointer, right? And you can do all your code, and then you can use this ptr own as mute to convert to convert your p to temporarily allow you to mutate your p pointer, and you do that by passing in this ownership token that says, here I have some raw pointer that I actually own. I'm telling you it's actually p here. I would like to update its value, right? And you'll have to prove that that is the case when you verify things with Creusot. And similarly, to even read your value, you're gonna have to do the same kind of proof. Right? And so this, again, we're leveraging the Rust type system again because we're using Rust's ownership mechanism to make sure that we can't duplicate this ptr own thing, right? We want that to be a unique token so that we're allowed to mutate, but we can't have 2 copies of it that allow 2 different people to start mutating this raw pointer, right? You can, if you actually do want to have shared alias mutable state, right, you can then store that in other sort of ghost objects that will allow you to share it. And in sort of a very separation logic style, you'll have to start reasoning about your invariants. There, yes?
So I'm
Yeah.
very good at Rust, and I definitely don't know Coma. This is Rust code.
Yeah, this is all Rust code, yeah.
And so you would take the source Rust and have them modify and
Yeah.
annotate it with these various
Yes,
things
yeah,
to be able to use unsafe.
yeah.
And then all the unsafety is kind of controlled by like this ghost. and
Yeah, yeah,
snapshot.
exactly. This would be the Rust code that you write.
Okay.
When you compile it with cargo build, you get something very like equivalent to the original unsafe code that we saw. When you compile it with cargo Creusot, though, it's able to check that this is actually safe, right? Because it has this, in some sense, all this ghost stuff is all the reasoning that you're doing in your head when you're writing this with these unsafe pointers. You're saying, I'm allowed to mutate this pointer p here because I just created it. I know I'm the only one to have it, et cetera, right? It's just the ghost stuff allows you to make these arguments explicit and tracked by the compiler and tracked by the verifier.
So maybe you'll get to this, but
Yeah.
presumably the Creusot is able to show like, oh, actually this is safe, like
Yeah.
in this case. And there's probably lots of cases that Creusot is able to show that. And then there's maybe some cases where it's actually unsafe and it's not able to show that ideally. Are you able to build whatever logic it is that is Creusot is using to determine the safety of this scenario just into Rust C directly? That way everyone can benefit, we can just use it safely, or?
I mean, this is a long-standing discussion in the Rust C community, basically about the role of verification and how integrated it should be. The issue is that the safety argument actually requires like a formal proof here, right? Like, because what you're saying is, I have this pointer P, and I'm saying that this mutable borrow of this own thing is a proof that I'm allowed to access P, right? And that's encoded in sort of the specifications of everything in Creusot. That is not something that you literally see written in the text. Like, the new function is annotated with some stuff that basically will allow this further call to succeed, right? And Creusot reads all of those and proves all those things correct, right?
So I guess you have to be kind of careful about how you use this, that Creusot is able to do this proof automatically. So it wouldn't just be, you'd have to still have some sort of different syntax at the Rust level so the compiler can be informed about how, oh, this is this extra bit of reasoning I should do here
Yeah.
to show this is safe.
And there is currently a project to add contracts to Rust, right? But the contracts that are currently being added are really just, you can write Rust expressions that are executed sort of automatically at different points in your program. The contracts that would be needed here are sort of like this ghost code notion, right, is a separate thing that is on top of that. I actually do think that there are language design features that you could implement in Rust that would allow you to have very similar things without needing contracts whatsoever. Be happy to talk about that offline because it's sort of a tangent. Yeah. So this kind of tooling is very powerful, right? Like this is basically embedding separation logic into your Rust program, and you can sort of get arbitrarily crazy with it. The problem is, in the same way that separation logic can get arbitrarily crazy and thus arbitrarily hard to work with, this can make verifying or even reading your Rust program arbitrarily hard. But it becomes possible all of a sudden, right? Which is already a step forward. And the nice thing is also this gives us really powerful tools for reasoning about concurrency, and that's something that the Creusot team is currently working on, is applying this to verifying fine-grained concurrent programs. But sometimes this can just be sort of too much overhead, right, and too complicated. So I'm going to give a very brief overview of a project I recently worked on called Jillian Rust. And the target of Jillian Rust is really verifying large amounts, or like larger scale mixed safe, unsafe programs, right? Very, very efficiently. And so the idea is that, again, we have these like Rust code bases where a very small fraction of the Rust code base is going to be unsafe, right? And so we've sort of talked about, for safe code, there's all sorts of tooling and techniques that we can use because we can leverage the safety of the Rust type system to simplify our reasoning, right? We can forget about memory, we can forget about pointers, we can forget about all these things. But then again, we're going to have these unsafe bits. And so rather than doing everything in a tool like Creusot, where we could do this ghost code and everything, but it's kind of tedious, the idea of Jillian Rust is we could actually use two tools, each specialized for their half of the problem. So Creusot being specialized for verifying safe code, and Jillian Rust being specialized for verifying unsafe code with appropriate techniques, right? And all we have to do is figure out a way to bridge the two, right? If they can speak a common language, then you can sort of split the verification there. Yeah, and so the idea is that we want to use Jillian Rust for this unsafe code. And I'm not gonna really go too much into detail here. I'm just gonna give a very, very brief idea of how it works. But basically, Creusot has this very pure kind of mathematical view of your Rust program. Like a vector is a sequence of values, right? An integer can be modeled by a mathematical integer, these kinds of things, right? And that is very useful because that's what SMT solvers like to use. That's like what Rock likes to use. It's the tools that we like to be using when we're doing formal verification, right? The problem is, of course, that's sort of a lie. It's an abstraction of the machine, rather, right? And so the idea is that instead, Jillian Rust is going to have this different view, much closer to the machine. It's built in separation logic. It sees that you have these pointers that are going every which way and everything, right? And what we want to do is just make sure that we can maintain that abstraction, that we can maintain that bridge, such that Creusot can ignore the nasty machine world of Jillian Rust, right? And Jillian Rust only has to focus on guaranteeing that abstraction. It doesn't really care what you do afterwards. So long as you can establish that abstraction, Creusot can take over and do all the more complicated, like the more complicated functional arguments of your program, the deeper properties in some sense, but because Gillian Rust has done all this heavy lifting for you already, right? And the mechanism that we use to separate these two is the specifications, right? So in Creusot, this is the idea being here, vec push, which is something that we're able to verify with Gillian Rust. We have some function here that has a bunch of unsafe code internally, right? And in Creusot, we can give this like very simple specification, which basically says, well, we require the vector to be to have at most u size max over 2 elements, or rather I size max, which is a requirement given in the Rust standard library. And we also say, after the call to push, self will hold whatever it had before with the value t appended to the end. Right? This is, again, working at a very high level. We're saying a vector is a sequence of values. When you call push, you just add something to the end of your sequence of values, right? Gillian Rust can sort of de-sugar all this and see a much more complicated sort of separation logic view, which says, okay, at first you have to have some ownership predicate, something that describes the memory resources of your vector that is modeled by some value. You also separately have to have a disjoint ownership predicate for the value, again with its own model. You have to have this pure fact about the vector, about the lengths of this model, right? And then afterwards, I'm going to guarantee a specific pure fact. And it should actually also, yeah, that is actually correct. Yeah, and so it's going to have all this stuff, and we basically go through and we developed a compiler for the specifications, for Creusot specifications, which are able to de-sugar them for a lot of these functions into the form that Gillian Rust expects. And then internally, Gillian Rust can go further and add more fine-grained separation logic arguments for helper functions, things like that. And so using that, we're able to verify libraries that involve a lot more unsafe code than what we saw before, where we're not just doing one pointer manipulation, but we might have hundreds of lines of code that is primarily unsafe. Again, things like vec, potentially things like mutex, these kinds of things, right? Skip lists, vec deque, etc. And because Gillian Rust is a tool that's specifically focused on verifying this kind of code, it can ignore a lot of the other things that Creusot has to take into account. Like Gillian Rust doesn't reason about any sort of higher properties. It doesn't really have support for quantifiers even, things like that. On the other hand, the nice thing is that you get really good performance. So we can go through the like 500 lines of vec or whatever and verify the whole thing in about 2.7 seconds. So by combining these things, we can split the problems and allow each tool to sort of do its own specialty, really focus on what it's good at rather than trying to do everything all at once. And so long as they agree on that boundary between the two worlds, then we don't really care what the other tool is doing, right? Each one can sort of abstract over the other. Yeah, right. And so this is basically, you know, the end of what I have to share with you today. So quickly, some things have been proven in Rust using Creusot. So first is this project Creusot, which was proven by Xavier, who's now at AWS, where he wrote a CDCL stat solver, proved it correct, and taught himself verification in the process. And was able to get a stat solver that actually registers on the StatComp benchmarks, right? So this is not just like a naive stat solver. The whole point is that he's able to do all the optimizations that you do when writing a stat solver, all these kind of complicated things where you have indices into side tables and things like that, and still manage to pull out a correctness argument for things, right? And so that shows that like the idea being we want to avoid the compromise between verified and performant, right? And we want to do this while also not sacrificing idiomaticity of our programs, right? We want to be able to write idiomatic programs that are also verified and also performant, right? During my thesis, I also worked on Sprout, which is a very, very, on the other hand, is not a performant tool, but it's technically an SMT solver in the sense that it does both Boolean logic and linear arithmetic as another sort of benchmark for Creusot. And the Creusot team now also maintains Creusot examples, which has several, I think like I want to say over a dozen different kind of data structures in there that are all proven correct. some which use unsafe, some which don't, all these kinds of things. But each time attempt to push both the like idiomaticness of the Rust code and also avoid making sacrifices for the sake of verification. All right, then finally, so of course, like what I showed you today is still a fragment of Rust. In particular, we didn't really talk about concurrency. Today, concurrency is not something that we really support in Creusot. We have some very, very bare bones support, but it is very much a current objective of the Creusot team, which is working on extending the kind of reasoning that we do for iterators to things like futures, and then using all this sort of ghost code to also enable reasoning about concurrent code at a very fine-grained level. And we also have a nascent sort of IDE extension in VS Code that helps build a much nicer interface for verification, and we're working a lot on the actual experience of verification, how you iterate through proofs, how you debug proofs, and things like that as well. All right, that's all I have. Thank you very much.
So we've got like maybe 10 minutes to have discussion about that. I might lead with Creusot. How would you rate the user experience to being able to get into formal methods for a Rust user that previously hasn't come from a formal methods background? Because I think we can all agree that it'd be nice to get people on board and being able to do this sort of stuff.
I'd like to say it's really good. I don't think it's really good. I do think it's improved a lot. So I think maybe on a scale of 10, if I'm being generous, I would say 5. The issue is that formal methods is also just, there are obviously the aspects of like this is an academic tool and all this kind of polish is still ongoing. But also, I think fundamentally, formal methods is a different practice than programming, right? The formal verification is a different discipline. And coming into it with no like a formal background into it can be challenging just because you have to change the way you think about your programs, right? And what it means for a program to be correct and all these things. And all of a sudden you have to care about, you have to argue for the correctness of things that seem completely irrelevant just because internally you have to actually, the tool's stupid, right? Like the tool only knows exactly what you tell it, right? So you'll have to explain to it that, oh yeah, when you did this loop, you just stored all the elements in this specific order, and that specific order is relevant to why the final result is correct or something like that, right? And so you have to make all these arguments. You have to spell out all these details that you don't want to care about. And I think that's sort of always going to be a challenge for new practitioners. At the same time, we've been trying to push a lot on how many of these barriers we can remove. So things like recent support for inferring specifications of things like closures means that you all of a sudden can trim a lot of this kind of fat from your proof. So I would say so-so, but getting better.
How about the invariants and people having to be explicit about that?
Yeah, so they do have to be explicit about that. But the cool thing is if you're using iterators, then all of a sudden you don't have to be explicit about it, right? Yeah. Yes, Yad.
How the ghost type is defined?
At which level? Like literally in Rust?
Yes.
If I recall correctly, it basically gets compiled away to phantom data of the type. I mean, I have the code base, so I can pull it up, but.
Like from the Creusot, in the Creusot mode, like how is it leveraged?
In the Creusot mode, it's basically compiled to the, like ghost of T is compiled to T. Right, like it behaves in every way like a T, except we do add some additional checks to show that you don't leak. Like you have to have this erasure property, right? So you have to show that your ghost T can't influence the execution of your program in any way, right? So we have a static analysis that checks this property on your code before doing verification. And if that property is true, you're now safe to sort of treat the ghost T as a T, right? Yeah.
Is that static analysis that's built into the code gen?
Yeah, basically before CodeGen, but in Creusot, yeah.
Is that strong enough to verify the safety of some of these unsafe blocks that just that one analysis alone?
I don't think so, no, but I think in some very simple cases, we could build a static, and we could extend it to be able to handle those kinds of things.
Like in the example in the slides.
Yeah, Yeah, I think, well, again, the issue here is that there's an identity thing, right? Like, basically, internally, you can see this as having like an identifier. Like, you can see basically, you could imagine that inside of here, you're storing the address of this pointer, right? And then when you call this function, you need to show that this address is the same as this one, right? That's basically what it's doing internally. So static analysis wouldn't be able to necessarily do that on its own, but you could make a fancier one that could, right? For these kinds of simple cases. Yeah. And Mike? Yeah.
So just coming back to the ghost
Yeah.
picture, how does this work with calling functions on ghost variables? Do you need to like mark some functions as ghosts, or can you do it for
You can pass ghost variables to regular functions as well. We do also have a notion of ghost functions, right? So yeah. So and the two sort of have obviously separate uses, right? If you have a program function that has a ghost variable, yeah.
It sounded like you said you could mix ghost code with implementation code.
So I mean, you interleave it, right? But at the end, like we on the side show that the ghost code can't interfere with the execution of your implementation, right?
You can't have like a ghost variable pass as an argument.
You can, because when you compile it with cargo build, that becomes like unit. That it's an extra argument. You have to specify it, even in unverified code, but it's trivial. Like it's.
So it's the borrow checker succeeding is part of your like trusted computing base.
Yes.
So does that mean that you take as input the mirror?
Yeah. This is Creusot is built as like an extension to the Rust compiler, and so it takes in the mirror. It assumes the borrow checker is correct. It assumes that basically the early stages of the Rust compiler themselves are correct, right? That you have a faithful representation of your source text, all these things, right? I mean, my personal opinion on this is sort of that, like, scientifically, it is important to reduce your TCB, but I don't think that's where most of the bugs are. Like, the Rust compiler is pretty stable and pretty bug-free, and if I was gonna pick where I want to spend 10 hours of my time reducing bugs, it wouldn't be in the Rust compiler, right? Like, in a verification context. Yeah. Yeah?
I'm more curious about the mechanics of how you get the mirror out. That's something we've been working on as well, so.
Yeah, no, not a CodeGen backend, Rusty plugin, or Rusty driver, sorry. Yeah.
Except nothing goes out. So the analysis runs in the plugin.
Yeah. Yeah, in the end, we literally have a single binary you can call cargo build, or cargo Creusot, right? And that's the thing.
Regarding the integration of Jillian and Rust, one of the challenges is that sometimes undefined behavior could occur outside of an unsafe block. Is there anything that you guys do to handle this case?
Yeah, I mean, that comes down to the specifications that we give, right? So it is kind of an interesting thing, right? Because like if you're working with, one of the things is you might work with raw pointers and then return a mutable borrow, right? Like the implementation of index mute on a vector does that, right? You take your mutable borrow to your vector, you turn it to a raw pointer, you do some arithmetic, and then you say, aha, this is actually a mutable borrow to an element, right? Boom, right? And sort of magically, you now have this thing that says, for this whole lifetime, you can use this mutable borrow. But how do you know that you're actually, that's stuff in the future, right? Like that's outside of index mute. How do you know that the safe code is going to use it, right? And so the reason that we're able to do that, it comes down to the specific definition of that own predicate for mutable borrows. And so basically what you end up having to do, in short, in the definition of the own predicate, you end up having to prove that at the moment you're creating your mutable borrow, you have the permissions to, you actually are able to return a mutable borrow that will last that long. So you basically prove things about the future in your unsafe code in Jillian Rust. But yeah, it is also, there's, as Ziad mentioned, the reality is unsafe is not about unsafe blocks, right? And if Ralph Jung, who has written a lot about Rust and done a lot of things for the Rust community, has this blog post about like the scope of unsafe. And basically, you know, his argument is unsafe isn't even scoped to unsafe functions, right? The scope of unsafe is the whole module, is the whole abstraction barrier, right? So within VEC, like you can have a safe function that is manipulating values that are not actually fully well defined so long as that function is private, right? Like If you have a private helper function, it could be you could be passing along uninitialized values, and that's actually fine. Because again, like UB is also, it's a dynamic property, right? Yeah?
But this is only in the context of unsafe is being called somewhere already, right?
Yeah. But the point is that just because you have a safe function, like the scope of, it's not that when you exit the unsafe block, you have to prove that everything is safe, right? You can leave things in a weird state. The question is more like, at the abstraction barrier, are your public safe functions guaranteeing the properties that they should be, right? And internally, the scope is wherever, right? Like at any point you can break your invariants, you can leave them broken and repair them 500 lines later or whatever. Yeah. All right. Yeah. Oh, I think.
Wondering on the code you are writing with a database, do you think Creusot can apply?
Not yet. No, because unfortunately, and that's sort of one of the reasons that, like, I think concurrency is a big subject for Creusot, is that it's a concurrent software, right? It's highly concurrent. And so you need to be able to reason about concurrency as ergonomically as we can about iterators, basically, before we can even try tackling that. Oh, it's because I mentioned that I work for a database that's being written in Rust now, and we can't apply Creusot to that database yet, just because everything is super concurrent, and despite being safe Rust code, we can't handle it. Yeah. Well, thank you.